In this video, I'm going to show you how to use the coast down run-up test in the DT6 in order to get a bode plot, Nyquist, and phase response for the coast down or run-up of your various machines in order to analyze the resonance up to the maximum running speed of your machine. So the first thing you're going to do is toggle over to modules. Make sure you have the tact over here with your DT6. You can see it right here. Here's my laser tact. And I have it pointed at the shaft on some optical pickup tape that I have. Then you're going to want to tell the system you have the TTL so that you can see the coast down, because you can only do this if you have a laser tact. So you're going to go ahead and press that. Then it's going to ask me if I want to acquire data or load data. In this case, I don't want to look at an old file. I want to actually take data, so I'm going to go ahead and hit acquire. Then it's going to ask if I want to do a run-up or coast down. I'm going to tell it I want to do a coast down test because you're going to want to do whichever one takes longer for your machine. And for most machines, a coast down is longer, which means you'll have more points and better resolution. So now I'm going to go ahead and get my machine up to speed. And then I'm going to go ahead and press this OK button. And once I see data show up, then I'm going to turn the power on. So I'm going to go ahead and press the button. Then I'll turn the machine off, and it'll automatically just start taking data. Up here at the top, we can see the speed as it decreases down as a function of time. Here we can see the amplitude response for the blue sensor vertical and the corresponding phase response for the blue vertical sensor. And we can go ahead and toggle through the tabs. It's not going to let us do that right now, though, because it's going to want us to finish taking data first before it actually lets us start toggling and doing analysis on this, just for the sake of memory. The system will automatically shut off once it gets to a speed at which point the accelerometers tend to start being dominated by noise. So you can just go ahead and let it sit for a while until it stops taking data, and then you should be able to just look at it. So right here, just off the bat, we can see that there's probably a resonance here at 1200 RPM. And it appears that there might be another one over here somewhere at, let's say, 900 RPM. Once it's done taking data, we should have a, it should automatically stop. So now we've taken all the data set, we can see it. So you can take the cursor on the phase one and drag it across, and as you drag it, you'll see the phase plot in a kind of phase balloon diagram shape. And as you move it, it'll move the phase cursor. So the first thing we can do is we know that for a resonance, if the phase shifts 180 degrees, we've gone through a resonance zone, and wherever the 90 degree was, that's where the center frequency of the resonance is. So as we sweep here, closer to this high resonant amplitude, we can see if we can confirm it. And sure enough, right here, we get a noticeable phase change of close to 90 degrees. So what that tells us is that there's actually probably another resonance around here somewhere, because we only got a 90-degree change. And for a full resonance zone, there should be a 180-degree change. But as we keep sweeping across, we can kind of see that there's another phase change right here around this one. So we have another resonance right there. We can also toggle to the other channels and look at them as well. So we can just look at the phase, see here, we can get the amplitude readout right here, and then you have the corresponding. You can also use this one at the bottom to sweep across, if you'd like that more. You can also hit the play button, and it'll start from this side and slowly sweep through automatically. So we can press that, we can see. And again, we're looking for a 180-degree shift, and it might be a little hard to tell, but when we were right here, we're kind of in this bottom portion. And as we get to the top of the peak, we've effectively turned from here to here, 90 degrees. So that confirms that this is in fact the center of that resonance. And as we sweep past it further, we get a continued up to this region when we started over here. So that's the rest of our 180. So we can confirm that this right here is one resonance. And if we keep sweeping it, we can see that in this region, right here, the phase, is actually going the opposite direction. So when we were sweeping up this way, we had a very clear counterclockwise motion. And then when we go here, we have this drop right here that goes the opposite direction. So it's a little hard to tell, but now we're going clockwise. Whenever the phase starts turning the opposite direction and there's low amplitude, that points to the idea of having an anti-resonance there. Anti-resonance is a little confusing, but it's basically the exact opposite of resonance. Instead of making the vibration significantly larger, it makes it significantly smaller. So if, for instance, our machine was running at 1200 RPM, if we could either slow it down to 1100 RPM, we would get a significant decrease in the amplitude of the vibration. Or what we could try and do is stiffen it, and if we stiffen the machine, the effective resonance curve should slowly shift up, and we can potentially shift this low point to the 1200 RPM and actually get rid of a lot of the vibration just by stiffening it and moving this low point, which might even be an anti-resonance, to over here. We can toggle through the other channels and look at them as well. We can see here that we have this one is the blue axial, and very clearly we have a resonance here and one here. And if we sweep across, we can see, yep, there's a 180-degree shift. And roughly right there is another one. We can also toggle over to the Nyquist Plot, which just gives you an idea of what the Nyquist Plot is. Nyquist Plot is sometimes a little hard to understand, but it roughly describes the actual motion of the vibration. It's a plot that describes both the amplitude this way and the phase around. And what you're looking for as far as resonances is anytime the circle, it makes a half circle all the way around. So it goes from one side, let's say 90 degrees, down to 180. That's a resonance. And you can also, if you follow the path of where it started and go around, if you see two subsequent circles that are on the same side, you know they're both resonance. But if you see one circle and then a circle on the opposite side, the one on the opposite side is likely an anti-resonance because its phase is effectively turning the opposite direction. So that's one kind of useful feature. The last thing I'll mention really fast is some people like to look at the amplitude in terms of decibels. So you can go ahead and set the decibel gain value right here. So in this case, 0.1. And then if I hit decibels, it'll shift the graph so that 0.1 Gs in this case corresponds to a decibel value of 0. And then it re-puts the scale on a decibel system. This is useful because if you toggle through and you find a region like this one, for instance, where there's a very significant peak right there, this would likely be an anti-resonance, and we can try and confirm it with the noticeable phase discrepancy that we have right there. This is probably some sort of anti-resonance. And in the regular scale, it gets close to 0, but we can't tell exactly how sharp it is. So if we switch it to decibels, then it will accentuate any sort of peaks that it has, and the sharper they are, the more resonant they are. So I hope this helps. If you want, you can save this data, hit the save button. I'll just go ahead and call this resin. I'll just use the default name. I'll change it to today's date. And then I hit OK. And then it goes ahead and saves that data. And then we can return, and we're done. And that's it. And then we can, if we wanted to look at it again, we could just click the codes down button, and instead of hitting the acquire, we could hit load. Go ahead and load one of those old files and take a look at it. But now, I hope you can see that the DT6 is a useful feature in order to test for resonances present less than running speed, which is often one of the most dangerous times for a machine is when it's first being powered up, first being turned on. That's where a lot of the time you get potential catastrophic failures or the initial sort of impact event that caused a bearing problem, whether it's stage 2 or stage 3, etc. But I hope this video has been helpful. As always, if you have any questions, feel free to contact us. Thank you.